Now next step is step number 7. Next step is step number 7. So step number 7. The next step is design for bending tension in longitudinal direction. That is design for steel. So design for bending tension in longitudinal direction. In longitudinal direction. Now that is AST calculation. That is AST or steel calculation. Now we have a AST for negative bending moment or hogging moment. Now the formula for calculating the AST, it is already known to you that AST is equal to 0.5 into FCK divided here by Fy multiplied by 1 minus square root of 1 minus 4.6 mu divided by FCK BD square and it is this complete term is again multiplied by B into D. This complete term is again multiplied by B into D. Now we have the value of mu for this particular negative bending moment or hogging bending moment. Now we have this mu is equal to 15 minus 1500, or we can take directly 1500 kilonewton meter, 1500 kilonewton meter. Therefore this value AST, this is longitudinal steel at the top. This is longitudinal steel at the top. Okay. Therefore this will be 0.5 into FCK is we have FCK is equal to 25, Fy is 415. FCK is the characteristic strength of steel. Fy is the characteristic strength of FCK is the characteristic strength of concrete and Fy is the characteristic strength of steel. Okay, and then we have 1 minus under root 1 minus 4.6 into mu. We have mu is equal to 1500 into 10 raised to power 6 Newton mm divided by FCK is again 25. We have B is equal to, that is width of footing is 2400. We can consider this as BD square, capital BD square multiplied by 1040 square and again this whole term multiplied by again we can consider this as small b, that is the width of footing. Okay, this should be considered as capital B. Therefore 2400 multiplied by 1040, so steel comes out to be 4109.04 mm square. Now we use let us use 16 mm 5 bars. Let us use 16 mm 5 bars, that is diameter of bar we are considering 16 mm. We are considering the diameter of bar as 16 mm. Okay, let us use 16 mm 5 bars. Let us use the 16 mm 5 bars. Therefore the spacing required, this will be equal to area of 1 16 5 bar area of 116 5 bar multiplied by width along which it is across which it is to be laid, okay, divided by area of our steel bars. So this is equal to area of 116 mm 5 bar is pi by 4 into 16 square. We have B as 2400 divided by area of steel. Area of steel is 4109.04. So the spacing comes out to be 117.43 mm. Okay, therefore spacing required. This is the spacing required, that is 117.43 mm. Therefore, number of bars, this will be equal to 4109.04, that is area of steel divided by area of 116 mm 5 bar, that is 5 by 4 into 16 square. We can say that is AST divided by area of 116.5 bar, area of 116.5 bar. Okay, so this total number of bars comes out to be, this will be equal to 20.44, that is approximately equal to, on higher side, 21 numbers. So we'll be providing 21 number of bars at the top face. We'll be providing 21 number of bars at the top face. Okay, along the length of footing at top face, Okay, so but we'll be providing, let us consider, since therefore provide, okay, therefore provide 16 mm 5 bars at 110 mm center to center, or that is 21 number of bars at top as hogging reinforcement or negative reinforcement, hogging or negative reinforcement, negative reinforcement. Therefore now AST minimum should be, now AST minimum AST, as we know that we provide 0.12% of cross section, of cross section area. Okay, so that is equal to 0.12 divided by 100, that is 0.12%, multiplied by, we have area is equal to 2400, that is B, multiplied by depth of our footing. Total depth was 1100. Therefore, this is equal to, since this capital D is equal to 1100, this AST minimum comes out to be 3168 mm square. Okay, let us again provide, we have got this AST minimum, provide 16.5 bars, okay, therefore number of bars is equal to AST minimum divided by area of 16 mm diameter bar. So it is equal to 3168 divided by area of 1 pi bar, 16 mm pi bar is pi by 4 into 16 square. So just scroll up. So this is equal to 3168 divided by area of 116 mm 5 bar is 201.06 mm square, and this will become equal to 15.76 numbers. Okay, so that is nearly equal to 16 numbers. So 16 numbers, 5 bars, 16 numbers, 16 mm 5 bars. Okay, hence what we will be doing, out of these 21 number of main steel bars, 5 bars can be curtailed from the point of contraflexure, say from at a distance 1.6 meter from both the ends. Okay, because the main AST steel requirement is within the range of your negative bending moment only. Therefore, hence, out of 21 main bars, 5 bars can be curtailed from the point of contraflexure. Okay, that is at a distance approximately, it is I think 1.585. So let us consider we are curtailing at a distance 1.6 meter, at a distance 1.6 meter from both edges. So we'll be providing the top bars in this manner for top reinforcement along the longitudinal direction, that will be, sorry, it is not aided probably. Okay, if we consider the plan, the top reinforcement will be, okay, the top reinforcement will be provided like this. Sorry. Okay, so this is our top reinforcement. How we will be providing it? Will be, this is top reinforcement, that is negative reinforcement. Okay, negative reinforcement. So what we will be doing? We will be providing some number of bars, straight bars, then again some number of sorry. Okay, just a minute. So what we will be doing? We will be providing some steel bars like this. Okay, sorry. Okay, let us provide some steel bar like this. Just a minute, yeah. Okay. If this is our footing in plan, let us consider this is our footing in plan, then the top reinforcement will be something like this. Okay, why it is? Just a minute. Okay. So the top reinforcement will be something like this. We will provide one bar like this, against another bar like this. Okay. Then we will be curtailing one bar. Okay, at a distance 1.6 meter from left and 1.6 meter from right, because this is the longitudinal steel reinforcement, and this is mainly required for the negative bending moment, whereas for positive bending moment from point A to C and B to D, only 16 number of bars are required, and from point A to B, that is from this column center A to B, will be requiring total 21 number of bars, whereas from this point A to C and from this point B to D, we require only 16 number of bars. Okay, so out of this total 21 number of bars, we can curtail 16 number of bars. So same thing we are doing here. We'll be providing some bars like this. Again, we'll be providing some bars like this. Again, we'll be curtailing one more bar. Okay, similar at the same distance. Again, we'll be providing some steel reinforcement. Again, we'll be providing some steel reinforcement. Again, we will be curtailing one more bar. So this is how we have to curtail total 5 number of bars. So this is how we have to make the arrangement for top reinforcement. Okay, this is only in longitudinal direction. Still we haven't calculated the steel reinforcement in the transverse direction. Okay, now we'll move to the positive moment reinforcement. Okay, now we'll move to the positive moment reinforcement. Now the positive moment reinforcement will be required to be provided at the bottom face of your footing. It will be required to be provided at the bottom face of your footing. Therefore, positive moment reinforcement, reinforcement calculation. Okay, so positive moment reinforcement calculation. Now we have maximum positive moment. We have positive moment or bending moment, can consider it as a bending moment, is equal to 500 kilonewton meter. 500 kilonewton meter. Therefore, steel requirement AST is equal to, formula is again same, 0.5 multiplied by FCK upon Fy. FCK upon Fy, again it is multiplied by 1 minus square root. 1 minus square root, we have formula 1 minus 4.6 mu, 4.6 mu into FCK BD square, BD square multiplied by B into D, multiplied by B into D. Put the values, known values, we get 0.5 into FCK is 25, Fy is 415, then bracket 1 minus square root of 1 minus square root of 1 minus 4.6 mu is 500. Okay, multiplied by 500 into 10 raised to power 6, converted it into Newton mm. FCK is 20. We have B as 2400, D as 1040 square, and then it is multiplied by 2400, and again it is again it is multiplied by D, that is 1040. We get this AST is equal to 1344 mm square. 1344 mm square. This is less than AST minimum. This is less than this is less than AST minimum, which we have already calculated. This AST minimum was 3000. This AST minimum was 3168 mm square. Okay, therefore provide positive reinforcement that is AST is equal to positive reinforcement AST is equal to 3168 mm square. Therefore again providing 16 mm 5 bars, 16 mm 5 bars, again providing 16 mm 5 bars. Total numbers will be 16, that is already calculated in for hogging bending moment. Okay, for the width B equal to 2400 mm. Now under we should provide some reinforcement under the columns also. We should provide some reinforcement under the. Okay, so these bars are required to be provided for positive reinforcement at the bottom face. But at the same time, these reinforcements are provided in such a manner. These reinforcements are provided in some band. Okay, below the columns. Okay, how I will show this. Okay, let us consider this is our one of the columns. This is our one of the columns. Okay, okay, let us consider this is our one of the column. Okay, and this is the portion below this column. Okay, this is the portion below this particular column. Okay, now the steel reinforcement is provided in such a manner that like this. Okay, this is having 45-degree angle. This is having 45-degree angle, 45-degree angle. This is the width of our column. This is the width of column, and as this is 45 degree, therefore this will be D, this will be D, this will be D, this distance will be B, this distance will be B, and this distance will be again D, that is effective depth of your column, sorry, footing. Okay, so these bottom reinforcement are provided in this particular region. Okay, this reinforcement are provided in that is these 16 numbers 5 bars will be provided in this region, in this band, in this particular band, having total width is equal to B plus twice D, B plus twice D, B plus twice D. Therefore, these steel reinforcement, these bars are to be provided in a band of width equal to B plus 2D, that is equal to, we have B is equal to 500 mm plus 2 into depth is 1040 mm. So this is equal to width of band width of this band will be equal to 2.58 meter, 2.58 meters. Okay, therefore we will be providing 16 number of these 16 mm 5 bars. Okay, up for a width of 2.58 meters only, and then 50% steel reinforcement will be curtailed. Now to calculate the spacing. Spacing of these 16 number 16 5 bars. The spacing of these 16 number 16 5 bars, spacing required is equal to again area of one steel bar multiplied by B divided by area of steel provided, that is pi by 4 into 16 square multiplied by 2400 divided by 3168. So we get this spacing required is equal to 152 mm. 152 mm, that is nearly equal to 150, sorry, 150 mm, that is nearly equal to 150 mm. Okay, that is nearly equal to 150 mm. Therefore provide 16 phi bars at 150 mm. Okay, that is 16 numbers, again 16 phi, 16 numbers. Okay, for a distance, for a distance 2.58 meter bandwidth. Okay, that is the same bandwidth below columns C, A and B, sorry, A and B. Okay, A and B. Just a minute, I'll scroll up. And then half of these bars and half, and then of these bars, half of these bars should be curtailed beyond this bandwidth. Okay, so for bottom face, for bottom face, okay, how we will be providing these steel reinforcement, I'll just show you. Okay, that is the spacing for this curtailed bars will be, spacing will be 2 into 150 mm, so that is equal to 300 mm spacing. Okay, so curtailed bars will be provided at a spacing of 300 mm center to center. Okay, again I'll stop this into shape. Just a minute. Now let us consider this is the bottom face of our footing. This is the bottom face of our footing. This is the bottom face of our footing. And then how we will be providing the steel reinforcement? We will be providing like this. Okay, how we will be providing the steel reinforcement? We will be providing one steel reinforcement like this, then another steel reinforcement like this. Sorry, one will be like this, another steel reinforcement will be like this, again curtailing half of the steel reinforcement. This will be up to end. Then we will have another steel reinforcement, then again we have one curtailed bar, again we have one full length bar, then again we have some curtailed bar, again we have some curtailed bar, again we have some full length bar here, we will be having some full length bar. Okay, again we will be having some curtailed bar here, again we will be having some curtailed bar. So these will be 16 phi at 120, sorry, 300 mm at 300 mm center to center, whereas this will be again one 300 center to center, but within this band, within this particular band of 2.58 meter, 2.58 meter band, will be having the steel reinforcement at 150 mm center to center. Okay, that is this plus this, both including these to uncurtained and curtailed bar. These will be at a distance of 150 mm center to center. So this is how we will be providing the bottom reinforcement. Okay, I'll delete this. It may create some confusion. Okay, now we have to design in the transverse direction. Now we have to design in the transverse direction. Okay, so consider step B, design for transverse reinforcement. So next step will be design for transverse reinforcement. Reinforcement, that is we have first designed the reinforcement in the longitudinal direction, that is along the line. Now we have to design along the transverse direction, that is how much will be the reinforcement along the transverse direction, that we have to design now. Okay, now we know that, as we know that I have already explained you that when we will be designing along the transverse direction, we will be considering that if this is our footing, will be, and this is the column. Okay, we are considering the transverse direction. Okay, some load will be acting over this. Okay, like this, uniform load will be acting over this, and this will bend like this will bend like this in the transverse direction, it will bend like this in the transverse direction. Okay, so how we'll be designing this? We'll be considering this as a cantilever portion which is resting on some column, and then we'll be designing this particular footing in transverse direction. Okay, so now in transverse direction, direction, the footing is designed as a cantilever supported on, which is supported on a column. Okay, therefore the transfer reinforcement provided in each column will be, again, that will be provided in that particular bandwidth only, therefore the transverse reinforcement is provided under main columns, or simply columns, within a bandwidth of again b plus 2d. Okay, where, or capital B plus, small b plus 2d, where this small b is equal to width of column, small b is width of column, and small d is equal to depth of footing. Okay, this we can consider this as effective depth only. Again, we have already calculated this bandwidth under each column, this bandwidth under each column this is equal to b plus twice d. So this is b is 500 mm plus 2 into 1040, so that is equal to 2.54 meter. So this bandwidth is 2.54 meter. Again, we have upward soil pressure, soil pressure, we have upward soil pressure. Okay, we need this in kilonewton per meter. Therefore this 1600 load on your column multiplied by 1.5 divided by 2.4 meters. So we'll get the upward soil pressure. This 1600 is the load on your column. This 1600 is the load on your column. Therefore 16 this will be equal to transverse load will comes out to be 1000 kilonewton per meter. 1000 kilonewton per meter. Okay, let me scroll up. 1000 kilonewton per meter. Now bending moment at the face of column in transverse direction. Now bending moment at face of column in transverse direction. Okay, this will be equal to this load 1000 kilonewton per meter square multiplied by the distance of edge of your footing from the face of column. So this will comes out to be 1000 multiplied by this distance will be 2.4 by 2, that is width of footing, by divided by 2 minus half of the width of column, and this will be square divided by again divided by 2. Okay, so this bending moment value comes out to be 451.25 kilonewton meter. 451.25 kilonewton meter. Hence provide minimum AST, because the AST whichever will be coming from obtaining from this 451.25 kilonewton meter will be less than AST minimum. Therefore we will provide a minimum AST. We have AST minimum is equal to 0.12%. 0.12% of this bandwidth. This bandwidth is 2540 bandwidth multiplied by the depth of footing. So 1100. So AST minimum will be equal to 3353 mm square. 3353 mm square, providing 16 5 bars. Then spacing required, if we provide 16 5 bars, then what is the spacing required? Therefore spacing required, this will be equal to area of 116 5 bar, that is pi by 4 into 16 square multiplied by the width in which this reinforcement is to be distributed, that is equal to bandwidth, that is 2540 divide or 2.54 meter divided by AST minimum, that is 3353. So spacing required is equal to 152 mm. Let us provide a spacing of 150